Sannikov will speak later, and instead of him, we will now have Professor Mukesh Singh Bori. I hope I pronounced correct. Yeah, right here from Samara, right? Yeah. Remote sensing. Very good.
Thank you.
Just start.
Good morning, friends and dear colleagues. Myself Mukesh, and before going to start my presentation, I want to briefly introduce myself. So I am senior scientist in Samara University as well as adjunct professor in American Central University, Colorado, USA. I also work as a scientist in Indian Space Research Organization as well as NASA, and as a faculty in different countries like India, Czech Republic, Germany and Japan. I complete my bachelor and master degree from India, then pre-doc from Catholic University, Leuven, Belgium, then PhD from Brazil, postdoc USA, and also visit UK as a honorary fellow. I have some distinguished awards or fellowships like Academy of National Research, National Academy of Sciences Fellowship through National Research Council, Central Government of USA, Washington DC, also awarded European Union Fund, and Brazil, Italy Government Fellowship when I did my PhD, and Belgium and Indian Government Space Fellowship. I have around 100 plus peer-reviewed papers, including books as a first author. So last more than 10 or 12 years, I am working in remote sensing and GIS field. So this is my brief introduction, and today I want to speak something about space Earth observation and its application. So how we can utilize or use satellite data and what's its application, I will be explain about that. So in my whole presentation, I will be explain basic of remote sensing, its satellite remote sensing and aerial photogrammetry. About some parts of I will cover about remote sensing, then also digital aerial photogrammetry, as not only satellites, we can use aircraft also for collecting information. Right now, scientific community using hyperspectral remote sensing. It's new and advanced technology. So how it's better than multispectral remote sensing? So I will be explain about that. And in last, I work as different countries like Brazil, USA, Czech Republic, UK, Germany, Russia, Japan, and also work on Myanmar. So how satellite can be utilized for safe applications? So I will be explain application part where I did different work. So first, what is the remote sensing? When we eat something or we touch somebody else, so that is we are directly physical contact with the object. So this is not remote sensing, but I am saying something, you are listening me, you are watching the slides and collect some information. So this is the true remote sensing. So we can say remote sensing is the acquisition of information about an object, area or phenomena with some distance and without physical contact with the object. So when we are collecting information far from the object without touching, that is the remote sensing. Here remote sensing process is we can divide in two parts, data acquisition and data analysis. So you can see that here if sun is the source of energy, electromagnetic radiations pass through the atmosphere and interact with the earth surface. This energy may be transmitted, some energy may be absorbed by the earth surface, some is reflected. So around 4% energy is reflected and it is captured by the through satellites, aircraft or shuttles, high altitude shuttles. So this whole part goes in data acquisition, because how we can get the information. Second, they give two products in pictorial and digital format. Later on we reference that data, make them because it's a raw data and we convert it in a meaningful data. So raw data is converted in meaningful data and then we convert them in some thematic layer or some products, and then we will be used. So a lot of users are here like civil engineers, urban planners, environmentalists, geologists, geographers. Everyone is using satellite data or remote sensing technology. So last more than 10 or 12 years I am working in this field, and today I think that in each and every field we can use satellite or remote sensing technology. So as I told you, how energy or how information pass from one object to another object. So they always pass through electromagnetic radiations, and output is always a satellite image. We cannot get direct information from satellite image, we need some prior knowledge or experience. So, how we can image analysis and interpret it? So, we can collect the information from satellite data. So, this is the aerial photogrammetry, this is the satellite remote sensing. This is the most important slide in presentation. First, I will tell you something here that this is a spectral graph. We are human being and we can see only 3 colors, blue, green and red. So, if in vegetation we can see that around 20% reflectance is here. So, the information we can collect in visible range is only 20%. Once we go in infrared region, you can see that reflectance is around 50%, means we are getting just 50% information in comparison of 20%. So, here is too much information, but as we are human being we cannot see infrared region. So, we give some color to infrared to read the information. That is why always satellite image called FCC, means false color composite, because they are not true color. Here one more thing, that in water in visible range it has some reflectancy, but if water is clear then in infrared there is no reflectancy. That is why in satellite image water is always looks like a black color. This is the electromagnetic spectrum and we use always in visible range from 0.4 to 0.7 micrometer, also infrared, microwave and thermal infrared. We are not using X-ray and gamma rays and ultraviolet in remote sensing. I will also tell about hyperspectral remote sensing. So, in hyperspectral remote sensing we are using visible as well as near and short wave infrared region. So, this is the second part, atmospheric effect. When energy is passed through from sun to our earth surface and it is passed through the atmosphere, atmosphere always effect on the radiations and its main cause of the degradation of the quality of image. Like some radiations are absorbed, scattered and transmitted through the dust particles, gas molecules, clouds, and only some energy which is reached on the ground. They have two chances, either it will be reflected, maybe absorbed or maybe transmitted. So, only reflected energy is useful in satellite remote sensing. Here one more word you can see here, we can illuminate our target our own. So, we have some artificial source of energy and illuminate our target, and then the energy will be returned back to sensor, that is called back scattering. So, we have two types of process, one is the reflectance, so second is the back scattering. I will be tell you something more about it. This is the atmospheric window. You can see that only visible part can reach on the ground, some part of infrared region and microwave region also reach on the ground. So, the part which is the pass through the atmosphere and reach on the ground, that is really useful for remote sensing. So, here you can see the whole process of remote sensing, that sun is the source of energy, then it interact with different objects like forest, water, grass, bare soil, roads, built up area, and then it is returned back to the satellites, and satellite produce always a image. As I know how to interpret how to analysis of satellite image. So, I can say this is the settlement area, vegetation area, forest area, water body, but for a new person he must have some experience period to reading the satellite informations or data. So, how we can divide remote sensing in 2 or 3 parts, like here. If the sun is a source of energy, we can call it passive remote sensing, but if we have our own electric source or our light source and illuminate the target and get back the energy, that is the active remote sensing. So, one advantage here, the passive remote sensing can work only daytime, because sun is only daytime, but if we have artificial energy source, then in night also we can work. Second, what part of electromagnetic radiations we are using, like visible or optical remote sensing. If we are using microwave part, we can call it microwave remote sensing and also thermal remote sensing. One thing here in microwave remote sensing, if the sun is the source of energy, it is passive microwave remote sensing, but if we have our own source, it is active remote sensing. The best example of active microwave remote sensing is radar. Always in radar we using microwave data, and it is active remote sensing. Third, also one more possibility, that if sun is the source of energy, but it is illuminated because some energy was already absorbed in the earth or on the ground. So, later on it will be go emissivity. So, if emission also collect by the satellites or by aircraft, that is called as a thermal remote sensing, or we can get the temperature of the object, like sea surface temperature, earth object temperature. As I told you, there is a two part of remote sensing in terms of one is the reflectance, second is the backscattering. So our satellite image also two types. Just here look that one is the sun is the source of energy, so it's based on reflectance. So if the surface is very smooth, this structure will be look is a very bright tone in passive remote sensing satellite image. Like radiations will become after interactions due to reflectance, it will be go due to smooth surface, that's it looks very bright tone. But same surface if it's have microwave remote sensing, due to smoothness there is very less chance to backscattering. So that feature which is looks very bright in passive remote sensing, it looks very dark in microwave remote sensing. Just assume another object, like one object is very rough surface like this, and when energy is come after scattering, they have more chance to back to the sensor. So that feature which looks very bright in microwave remote sensing. So we really need some prior knowledge to read the information, to read the satellite data. Is it microwave data, is it passive data, and so on. One more thing here, the output is always a satellite image which will be saved in row and column, and they have each pixel have digital numbers, that is so its reflectance, and then we convert it in a thematic layers and read and utilize the information. So till here I just briefly introduce you what is the remote sensing, what type of remote sensing, how it's connect or how it will be work. Second part I want to say about if we are not using satellites, we have some aircraft. Information also collects some type of remote sensing, that is called photogrammetry. Photogrammetry means photo measurement. So in place of satellites we using aircraft and they are collecting information. But it's not so easy like you are looking that from aircraft you are taking photographs. It's a lot of problems, lot of errors and displacements. I will be explain briefly about whole process. So first I want to say that in terms of area we can divide photogrammetry in two parts basically for aerial photogrammetry. First is metric and second is interpretative photogrammetry. Metric photogrammetry useful for topographic maps, orthophotographs, for real features identification or some military intelligence purpose. It's a limited area, but if we cover large area, big area or inaccessible area, we use different type of bandwidth and multispectral cameras, then that is called interpretative photogrammetry. It's for long area or big area coverage. And the output is always like useful for topographic maps, to making topographic maps, orthophotographs and digital elevation models, so that we can identify height information or terrain information. Right now aerial photogrammetry useful for land surveying, highway engineering, making some thematic maps like soil, forest, geology, geomorphology, traffic management, and the best use of aerial photogrammetry is for military purpose. Like just assume that we have two countries and they don't have good relationship. So one country have aerial photogrammetry, his aircraft will be moving inside his own boundary, but due to like synthetic aperture radar side looking, it will be collect the information from neighboring country border, what is going on close to the border. So it's like a military purpose of remote sensing. We are already in our own country boundary, but we are collecting information from surrounding country. In terms of photograph, we all again divide it like aerial photograph or terrestrial photograph, vertical and oblique photograph. There is not true vertical photograph, because lot of errors are in the photographs or and lens. So if lens is only 1 to 3 degree tilted, then we can say it tilted photograph. In oblique, if we see the origin means high oblique photographs, we can see the origin, but in low oblique photographs, we cannot see the origin. So we can divide the photographs also like that, vertical and oblique photographs. And in methodology, how to collect photographs, we can say in traditional method, like in earlier time, we have object, filter, lens, cameras, then chemical processing and get print the photograph. But right now we are using CCD, charge coupled device, memory sticks, computers to edit our informations or photographs and then print out them. Also carry them in pen drives. So digital method is much better than our old system. And each photographs have 3 points, principal points, which is the center point of the photograph, nadir and isocenter. If it's a true vertical photograph, all 3 points will be same, but it's not possible because there are a lot of problems, and in real situation there will be no any true vertical photograph. So, as I told you, photographs are two types of vertical and oblique photographs. So, advantage of vertical photograph, they have constant scale, we can use them and as a direction as they are orthophotographs, also used as a map, and best use is for stereo pair. I will tell you again and later on what is the stereo pair, and it is very easy to interpret. But some advantages also in oblique photograph, like they cover much more larger area, some features which is not familiar in vertical photograph can easily identify in oblique photographs, and in cloud cover situations they cover a more clear image. As I told you, the system is not so easy as I am telling you. There is lot of problems and errors in the photographs. So, like due to curvature of earth, moving of earth, sun angle, due to lens distortions. So, the photograph is not accurate what we are looking on the ground. One more error I want to tell you about, that is called displacement. Means our aircraft velocity is not constant as well as its altitude is not constant, and it's have errors, like if our aircraft moving in x direction, y direction or z direction. So, its pixel size will be different than actual size, but if we know the amount and direction of tilt, we can remove these errors and make the correct image or photograph. So, generally we are getting that type of photographs, means pixel is not open exact location as well as it have some moving. So, when we rectified it, that is called orthophotographs. In satellite remote sensing, when we are removing errors, and that is called rectification, means we using topographic maps and give them GPS points and then correct the image, that is called rectification. And once our satellite image is rectified, later on another satellite image can rectified with the same previous rectified image, and that is process called registration. So, So, the rectified photographs is called orthophotograph in aerial photogrammetry. Always we have now two types of photograph, digital and printed photographs. So, digital photographs are always good in terms of high resolutions, quick availability, digital image processing, reproduction is very quickly and low cost, and we can add information. That is why digital photographs is better. One word is also come here, stereo pair. So, when we are overlapping two photographs which is cover around 60% same steady area, they looks 3-dimensional view. So, simply 3D view called stereoscope, and the two photographs which is in pair, that is called stereo pair. So, what happens that if our flight is going in like this direction and every photograph covers 60% overlap area in front side or forward direction, and then when we make them on the table, they looks 3-dimensional. And for that, first we make some flight path. So, when our plane will be going here, its 60% cover overlap in front direction like that, and when it's returned back in second path, again it's 20 to 30% cover on side lap. So, these photographs when we arrange on table like this and see with stereoscope, it looks 3-dimensional, and we can measure height of the building, height of the terrain. So, it's 3D view of aerial photography. So, till here I just first explain you basic or brief of remote sensing, later on I explain you aerial photogrammetry. Now, last 2 decades or 3 decades, people use hyperspectral remote sensing. Actually, earlier first people was using traditional classification method to classify features on the object or measuring features and making topographic maps. They go in field, it is too much time consuming, very costly, and need too much manpower. Later on in 1970s, satellite remote sensing technology came, and people using satellite data to making topographic maps and for classification of the objects. In 1970, that time people using multispectral remote sensing. It's have around 7 or 8 bands. So, they have some limitations also, like we can identify, okay, this is the forest area on the ground, this is the agriculture or water body or settlements, but they are not identify what species in the forest area, what plantation in agriculture field, or what type of water, is it turbid water or shallow water. So, hyperspectral is cover all these disadvantages. So, how this concept come? Actually, in 1980s, that time some chemist and physicist or geologist scientist using stereoscope in their laboratory or in the field. In that, simply they have large number of bands, and if they have find reflectancy or with lot of like minerals, it says gold, copper, silver, magnesium, iron with the stereoscope. So we merge two technology. One is the satellite remote sensing. Second is what we are doing in laboratories or in the field. So cover the good advantage here using large number of bands of the characteristics of stereoscope and put in the satellite. So new thing was coming, hyperspectral remote sensing. So basic thing is difference is the large number of bands in hyperspectral remote sensing. When we are using large number of bands and they have narrow bandwidth, then each bandwidth will be sensitive for a specific object. They will be pinpoint the object due to lot of energy or due to their too much sensitivity. So now we have capacity to identify features in subclass level, and that's why now people are using for water, urban transportation and vegetation species identification through hyperspectral remote sensing, because it's detect directly biochemical or structural difference in the object. Here you can understand, like if we are using only 7 or 8 band in sensors, means we can collect only like forest, agriculture or water. But if we are using large number of band like 200 bands and with narrow bandwidth, and then they will produce a continuously spectrum. So we will get all information. Here if we using only multispectral, we can find only one graph, but if we are using multispectral, means 200 bands and every band is very narrow bandwidth, and due to this narrow bandwidth they are very sensitive for each object. So we will find out, okay, what type of soil is here, what type of minerals is here, and collect maximum information, and that's why we get all information on the what is on the ground. That's why recently when we sent some our satellites or some in another planet like Moon, we using hyperspectral remote sensing to collect all type of information which is possible maximum to maximum. So in multispectral we can get limited information, but in hyperspectral remote sensing we can get all information as a spectrum. So the basic difference in multispectral and hyperspectral is number of bands. Earlier we using only 6 and 7 bands, and the bandwidth was very broad, so it was not too much sensitive to identify the features. But now we are using more than 200 bands with narrow bandwidth from 5 to 10 nanometer, and it's also have Z direction showing spectral information. So one thing is, if it's have advantage, it's also have some disadvantage. Now we are collecting too much information which is really not so easy to analyze, not so easy to carry things or transmit it. We need big and fast computers. So if technology have some advance, it's also a disadvantage. We want more information, but again too much information is also a burden for us. So if we want to difference between two bands, two sensors, which is the real hyperspectral and multispectral, like I say that I have two sensors, one is the hyperspectral and another is multispectral, which is really true hyperspectral, and both have 20 bands. So I will directly look if it's both sensor have 20 bands, which sensor have continuously band and narrow bandwidth, that is really true hyperspectral sensor, even it's in visible range. But if another sensor which have 20 but all bands are not continuously and they are in visible, near infrared, short wave, mid wave or long wave infrared region, means they don't continuously even have same number of bands. So that will be called as a multispectral band or multispectral sensor. As I told you that it's very sensitive due to narrow bandwidth, so it's have more applications. In atmosphere we can identify water vapors, cloud particles, aerosols. For ecology, all type of features we can read and identify. In geology, to identify minerals and soil types. In multispectral, it's not possible. For coastal water, snow, ice, medical, some industries, one in coal, oil, hazardous and cement plants and food industry, we can use hyperspectral remote sensing. Also in environment and commercial purpose for mineral explorations, agriculture and forest area. in military purpose also using, you remember that last time Osama bin Laden was cast by US in Pakistan. So, the main thing was he was using hyperspectral remote sensing. He just give a specific watch or helmet to their soldiers, and they are very sensitive, and they continuously track where is their soldier is moving, and in last they know, okay, our soldiers are here. Right now people are too much shouting about chemical weapons, and again in hyperspectral remote sensing, it's very sensitive, can easily identify what is chemical on particular area and easily detect. So, when I know that okay, people using hyperspectral remote sensing in place of multispectral remote sensing, I also want to use at least one time for hyperspectral satellite data, and for that this is the Samara region, and I choose this study area due to availability of data, and did some research work to identify of lot of land core classes. Like here you see, I can in multispectral satellite data I can identify these 8 features, but I want to identify these 27 features. So, simply I go in field work. Also selection of data is important, because you can ask me why I choose this area, why I did not study on Samara region, because the free of cost data was available here, and resolution was also important parameter for me. So, I choose this study area, and my main motive was first build subclass level of classification. Second, I want to know is a hyperspectral really better than multispectral or not, and what classification is really good, supervised or unsupervised. And in last, I want to make a spectral library. Means if I know that gold have this much reflectance, a particular this wavelength, I can save this information, and later on if I get some data and it's a particular that type of reflectance, I can say, oh yeah, feature maybe is the gold or some silver or something like that on the ground. So, that is called a spectral library. So, I want to identify or read these things. So, I did hyperspectral remote sensing. So, I go in field work and around 60 training sites and collect satellite data, collect field work data. Data selection of satellite data was based on resolution and cost of the data. Third, pre-processing, as the multispectral data pre-processing was not so hard, just georeference data and remove some errors. But in hyperspectral remote sensing, as it have 200, I use Hyperion data here. So, Hyperion is 242 bands, it is too much. So, I just remove unnecessary bands which is not useful for me, and finally, only 132 bands I use in my study. Also use these two ALI and OLI multispectral data, use secondary data from field and ancillary data, making classification and ultimately find the results. So, in results you can see this is 242 bands in Hyperion hyperspectral data, and these are unnecessary bands. So, I remove, but in particular this range from 82 to 94 bands, I already dezoomed this graph. If I can, due to limitation of PowerPoint slides, if I will be enlarged, you can clearly separate out each 27 classes in hyperspectral data, and you can say, okay, if this is the feature in the ground, that is the particular object. But same thing, if I use multispectral data, particularly in visual range, I cannot separate the objects, but in infrared, I can separate around 12 to 13, but not possible to classify or separate out 27 classes. If I, in last I did for classification accuracy, when I compare with supervised and unsupervised classification, overall accuracy is high in supervised classification in comparison of unsupervised. And then when I compare only hyperspectral and multispectral data, everywhere I see that in producer accuracy and user accuracy, hyperspectral data have high accuracy. So, ultimately I get result that this is the classified hyperspectral data with 27 classes. So, ultimately I get result that hyperspectral data is really much better than multispectral data in terms of categorize the classes. We can classify till subclass level, but in multispectral data we can classify only 7 or 8 classes, and supervised is better than unsupervised classification in all type of data. And another thing is, if we collect field data in the same time of collecting satellite image, the accuracy will be really high. So, this is the, I think time is going fast. So, this is the development when first it was multispectral, then hyperspectral, then active and passive remote sensing radar development. So, USA, Canada, Europe, Australia, they are using hyperspectral sensors in their aircraft. For space technology, NASA, European Space Agency and Indian Space Agency using sensors in satellites to collect hyperspectral data. For another planet, they, India and the USA using their missions and using hyperspectral data. So, now till here I explain you basic of remote sensing, photogrammetry and hyperspectral, why it is better than earlier system. Earlier people using traditional method, then remote sensing, multispectral, now people using hyperspectral. So, as I work in different countries and I use satellite data or aerial photograph in different applications. So, these are the part. I will be go very fast little bit here. So, this was I derive vulnerability for natural, environmental and coastal vulnerability based on their parameters. So, what is the vulnerability? So, vulnerability means simply a risk. Here we have three parts: exposure, sensitivity and adaptive capacity. You can assume that we have a big water pond in our study area and it is a 10-meter water capacity. So, if water level is increased like 6-7 meter, we know if 10-meter water level come, it will be broken and area will be flooded. So, it is a disaster. So, the first situation when the water level is going to increase, that is called exposure situation, and once the water level come 9 or 9.5, it was the condition of sensitivity, and in last if the water level goes till 10, that is the called what is adaptive capacity. So, what we are doing to save our system or our city, what efforts we are doing here, that is called coping capacity. And if we didn't save our system and water level due to high water level, it is broken. We didn't reduce the water level, we didn't increase the water capacity of pond. So, what will be we do? We are human being, we never leave our system in broken conditions, even lot type of hazard, earthquakes, tsunami. Always after broken system, we always try to rebuild our system. So, what are doing after disaster, that is called resilience adaptive capacity. Here you can see the sensitive map of study area. So, in USA, I was working in NASA and using MSR data, it has 6 frequencies. It was really better than earlier data. My main target, our team wants that is it the temperature also showing the feature on the ground or not, and we find that if temperature is increased, it shows desert area. If temperatures go down, it shows vegetation. I also separate out water and land. So, as MSR have 6 frequencies, of which frequencies are actual physical land surface temperature, and I find that high and vertical vertical wavelength is actual physical land surface temperature, like here water, green, this is built up area, snow and ice, bare land. So, vertical and high frequency, so actual physical land surface temperature. I also try to classify the features through PR and GR combinations and find that GR is the same like NDVI results, PR start value from 0. We identify that if MSR data is useful for only 6 or 7 land cover classes for first level, it is a really good satellite data. But if we want subclass level, like then it is not a good quality data. We need to improve the quality of data, because here more than 2 or 3 classes come in particular one range. So, we get the result finally. Second study we did their snow cover variations in January, April, July and August, around 100% snow in different density, then it is in April. In July, it is only in northern hemisphere in only Himalaya region, and in October situation. For in terms of elevation from January, snow was 70% snow from 0 to 2000 meter elevation, it is in April. In July, maximum snow was after 5000 meter elevation, and in October it is come downside, and always after 7000 meter elevation it is constant. So, I did in Czech Republic, I identified these 3 sites, Olomouc, Jesnik, Križanec, and find out that if we go close to city, due to tourism they have So, in UK I did some sea surface temperature study. In Germany I did Kuala Lumpur, Malina and Singapore CD. So, CD density was increased continuously for every 1 kilometer distance. Here in graph you can see in city center density was more than 90%, but particularly in these kilometers from city center, first half density was increased, but second half density was not increased. Here is the big difference And you can see in these graphs that where city was grow and what is the built-up area in particular what region. In Samara, I also did same work, and the most important thing in Samara, the population and the built-up area was first increased, then reduced dramatically. So I compare with the populations, and I see that till 1991 or 2, population was increased, but later on till 2010 it was dramatically reduced, and again from 2010 to 2015 start to increase. So this is the map of which area built up in till what time. This is in Japan work, and I identified natural environmental vulnerability as well as if sea level, water level increase in the river, how much area will be covered and which class will be affected. Later on I was also working on Myanmar. It was around 43% is below poverty line and around 25% children under age of 5 are underweight. This is the dry zone area. So I want to know what is the main feature, why is the dry zone area, which is the environmental pressurized zone area. So I study some making some parameters and make their color relations. Some have positive relations, some have negative. Ultimately, I get result that due to flood risk, irrigation, population, and land use is the main factor. That's why it's a very highly environmental pressurized zone. I also make some further maps and derive harvest failure, land degradation, or erosion danger level, and find that around 44% is erosion danger level. Its 60% area harvest failure and land degradation is 58.59, and derive food vulnerability. So in food vulnerability, still 50% area is enough food, but 40% area is not secure, insecure food, and around 4% area which is here is very insecure of food. So I get that result. I check due to compete the market demand or food demand, people choose the close to flooded area as a agriculture purpose because it's very fertile floodplain and good access of irrigation water. So they compare the market demand of food. Thanks for your patience, and if you have any question, please let me know.
So thanks for keeping in time. It was a hard work, right? 65. Yeah. Any questions? Probably there are many questions.
Yeah, please.
No? None? Have you all also been working with thermal hyperspectral data?
Yeah, in USA I work on MSRE data. This is the thermal remote sensing data.
Okay.
And I identify actual physical land surface temperature because it has 6 frequency, which frequency so actual physical land surface temperature, and I get result that we always use high and vertical frequency, so actual physical surface. If it's a water body, how much is exact temperature? Also in UK I did this work.
Okay.
And using thermal data.
Okay. Thank you. So then we again.
Thank you. Thanks for your patience.
The next presentation will be by our colleague from Britain, actually born in St. Petersburg, right?
Yep.
Professor Sergey Sazhin.
Sazhin, yeah, that's correct.
Sazhin.
Yeah.
So from University of Brighton about modeling sprays.
Thank you. Oops. Right. Okay. So I will start with thanking the organizing of the conference for their kind invitation. And I should admit that this is not my first visit to this place. And I enjoyed every visit in the past, including this one. So since I was here last time, just last year, I'm not going to spend time on introducing myself. Basically, you know, as was mentioned by the chair, I'm a professor of thermal physics at the University of Brighton, and I was born and educated in St. Petersburg, but it was very, very long ago. For the last 30 years, I have been living in England. And my presentation will fit to section 3 of the conference. that is a mathematical modeling of physical technical process and systems. And more specifically on this second topic, mathematical modeling of physical process and phenomena, and mathematical modeling of technical systems. Having said this, I will try to present the results in a form which can be perceived by a much wider audience, that is including those who work in other areas. But remembering the restrictions of my time, I'm going to omit many technical details and focus just on the basic ideas of our approach. So that means that from the point of view of the presentation, I'm going essentially to scratch the surface of the problem rather than to describe it in depth. So if you have any questions and you want to discuss any problems after the lecture, you are very welcome to do this. Questions could be accepted both in Russian and English. Вопросы могут задаваться на английском и на русском языке. And this is the plan of my presentation. I will start with the background, and then I will focus on three specific areas. These are the areas on which our research program was focused during the last 2 years. So, and the results to be presented will be those who are already published in international referee journals. So these are the topics which I am going to cover. First of all, these are Lagrangian and full Lagrangian approach to modeling of sprays. Lagrangian approach is something that is well known, probably not only by people working in the area, by a wider audience, but the full Lagrangian approach is not really so well known. It is well known in people working in this specific area and mainly in the mathematical community. Then I will move to the approaches to modeling spherical and non-spherical droplets. As you know, that droplets are integral part of sprays. And then I will move to the third topic, which will be focused on spray heating and evaporation and ignition. And I will end up with discussing future challenges. These future challenges are not going to be exhaustive, and they will be mostly focused on my own research interests and the research interests of the colleague with whom I'm working. Now, what is sprays? So without moving to mathematical definition of sprays, it's something that you may recognize from your everyday experience. It could be sprays like environmental sprays, like rain. It could be sprays used in cosmetics, for example. And it can be used in fire extinguishers, and this list could carry on. So my interest in sprays is mainly focused in automotive applications. So our laboratory specifically focuses on designing the most efficient and the less polluting internal combustion engines. And for us, sprays will be predominantly automotive sprays. But the models to be discussed are expected to have a much wider range of applications, far beyond automotive sprays. And this is another picture of spray, where we can see some sort of fine features which were not clearly seen on the previous slide. For example, you know, we can see that the droplets which compose the spray can be spherical, and at the same time they can be very far from spherical. Also, what is important for the modeling of sprays in the automotive engines is to be able to model not only dynamics of sprays, not only heat and mass transfer process inside the sprays, but also the process of ignition. And so this is a typical picture which is predicted by our CFD code, which describes the temperature distribution in sprays after the ignition process. And here we have another image of sprays which shows spray formation, if you like. So you can see that initially the spray is injected as a liquid jet, which is disintegrated into ligaments and liquid sheets. And this area is known as a primary atomization area. Then ligaments and liquid sheets are disintegrated into larger droplets, and larger droplets are disintegrated into smaller droplets. And this area is known as the area of secondary atomization. And once these small droplets have been formed, then we have an area in which droplets are moving inside the carrier phase of the gas more or less independently with a very weak interaction between themselves. So these physics of these two areas I considered in one of my previous presentations which I gave in this audience, I think last year and 3 years ago. Today I will focus predominantly on these dilute and very dilute regions. So this is where my presentation will be mostly focused today. And then I will move to Lagrangian versus full Lagrangian approach. So when probably all of you know the meaning of commercial computation fluid dynamics codes. So they are widely used by most of engineering communities, even without understanding, the structure of these codes. But when you deal with the structure of these codes, then regardless of the company which produces them, is essentially based on two approaches. First of all, it is so the whole enclosure is divided into a number of computational cells. This number of cells could be enormous. It could be several millions of cells. And then inside each of these cells, the parameters of the carrier phase are assumed to be constant. So that means that they're the same in this corner and the same in this corner. But at the same time, they change when you move from one cell to another. And these change of parameters between the cells in space and time are described by partial differential equations for the carrier phase. And this approach is known as an Eulerian approach. Eulerian approach when you focus on specific areas in space. And then as to dispersed approach, it is also possible to use Eulerian approach to modeling dispersed phase, such as droplets and sprays. But the approach which is mostly used is known as Lagrangian approach. In the Lagrangian approach, you consider the dynamics of droplets, each individual droplets, or some groups of droplets inside each cell. And since the parameters of the carrier phase inside the phase are constant, then the dynamics of these droplets are described by the system of ordinary differential equations. And this is something that I will return to in the following parts of the presentation. And the problem with the Lagrangian approach is that when you consider the dynamics of individual droplets, it's fine, it works. But in most applications, including the applications to automotive engines, we need to know not only the dynamics of individual droplets, but we know the dynamics of droplet density. And here we have a trick. Here we have a problem. And this problem is that in order to get reliable values of of droplet density in each individual cell, you need to consider astronomical number of trajectories using conventional Lagrangian approach. And to solve the problem in Moscow University, it was suggested to use a different approach, which was originally called full Lagrangian approach, and then in a number of publications including those in England, in Proceedings of the Royal Society, it was coined, it was referred to as Osipsov method. So the basic idea of Osipsov method is that, we are not only considering the trajectories of individual particles, but we also treat the dispersed phase as a pressureless continuum. And we solve the problem, we solve equations not only for the dynamics of individual droplets, but we also solve the continuum equation for the dispersed phase. And these are the continuum equations which are presented in a more explicit form. So basically, these equations will allow us to get the value of droplet number density along each trajectory if we know initial value of droplet number density. And this actually, leads us to a completely different philosophy, if you like, of calculation of sprays. So if we use this approach, then we follow the trajectory of just one droplet, and along this trajectory, we can get the value of droplet number density in each point which is covered by this trajectory. So in this case, the number of trajectories to get a meaningful distribution of droplet number density can be reduced dramatically, many orders of magnitude, to get the same accuracy of the distribution of droplet number density. So in this case, the number of these equations is 24 in 3D and 12 in 2D. So these are the advantages of this approach. So first of all, the particle droplets are treated as continuum or a set of continua, and it makes it possible to calculate particle droplet number density from the continuity equation for the dispersed phase written in the Lagrangian form. This leads to dramatic reduction to computational time and improvement in accuracy compared with traditional Lagrangian approach. And then this approach has a clear advantage in the case of trajectory intersections. But this is compared with the Eulerian approach, because this advantage is not compared with the conventional Lagrangian approach. But at the same time, this approach has a number of limitations. First of all, it was developed and implemented in a very narrow range of parameters, mainly 2 dimensions, and at the same time, the effects of polydispersity of droplets formed during injection was not really considered in details. So there are some approximate models were developed, but these models are at the initial stage of their development. And then what is quite important from the point of view of underlying physics is that this method cannot take into account the interaction between the droplets. And then I will move straight to the applications. So what we try to do, we try to implement this method into computation fluid dynamics code Fluent, and then apply it to modeling of the process inside the gasoline engines. And here we have the number of trajectories, which was shown for about 10,000 droplets in these range of diameters. And here we have the diameter of droplets correspond to to different colors. And so you can see a rather complex picture of the direction, because the distribution velocity of the carrier phase was taken from the experiment. And then you have more clear trajectories of individual droplets. And at this slide, what is most important for us is that we have a droplet droplet number density along each trajectory. So as you can see, so here we have some sort of preliminary results, in a sense that we consider the effect of the carrier phase on the spray, but not the effect of spray on the carrier phase. So, the main objective of this work is to show that this method works in principle, and then potentially it can be refined before it can be recommended for industrial applications. And so the details are presented in this paper published last year in Atomization and Sprays. And now I'm going to move to the next topic of the presentation, which is focused on spherical and non-spherical droplets. So here we have a typical video which was obtained by my colleague in Sandia National Laboratories, showing the dynamics of individual droplets. So as you can see, these dynamics appears to be rather complex. So sometimes it can be spherical. Sometimes the shape of the droplets can remain spherical for a long time. And on other occasions, you can clearly see the formation of non-sphericity of droplets during their dynamics and during heating and evaporation process. So that means that we need to focus not only on spherical droplets, but also on non-spherical droplets. And some recent results obtained in this direction will be summarized below. So I should emphasize that all results which are presented in this lecture were obtained mainly during the last year and this year. They're very fresh, they're very recent. And first of all, what we've done about spherical droplets. So I'm not going to talk much about it, because this topic was the main focus on my previous presentation in this audience. But I just want to summarize some of the results which were reported. And I will start with the fact that we developed previously the model for multi-component droplet heating and evaporation. And then we applied this model to the analysis of automotive sprays, and we showed that its efficiency. Basically, this model is based on the analytical solutions to the heat transfer and the species diffusion equation inside droplets. And at this stage, we moved further, and this model was implemented into computational fluid dynamics codes Fluent. And then it was shown that it can work alongside with other models which are already there in this code. And I'm not going to spend more time on this. And then another topic which one which we focused was that we try to generalize our previously developed models for multi-component fuel droplets and heating and evaporation to the problem of droplet drying. So this problem appears as part of the project supported by Royal Society of the United Kingdom and the Russian Foundation for Fundamental Research. And it was a focus on our attempt to apply our models to other areas, for example, to the area of pharmaceutical applications, and the models developed for pharmaceutical applications were applied to automotive applications. And for example, in this particular case, we managed to develop further our model, which was originally applied for automotive applications, to pharmaceutical applications. Mainly, we were able to model the drying process. And we believe that this approach to modeling drying process is more efficient compared with what was suggested earlier. And although this paper was published just several months ago, we got a lot of feedbacks, and people start appreciating that this approach works. And now we will focus on non-spherical droplets. So the general modeling of non-spherical droplets is not really a very challenging task, because many people were working on it using various approaches to modeling the evolution of the droplet surface. For example, level set approach or volume of fluid approach. These are some of the most popular approaches to this sort of problem. But at the same time, we can apply this approach to modeling one or two droplets. In all our applications, we are dealing with the millions of droplets. To apply, for example, volume of fluid approach to millions of droplets is a hopeless task. It is a non-starter at all. So that means that we need to work out a bit of a compromise approach, in a sense that we need to develop a model which will capture essential features of the process, and at the same time would be simple enough for potential applications in computational fluid dynamics codes. And this model is focused on the assumption that the droplet initially has spheroidal form, and it remains spheroidal during heating and the evaporation process. This is a key assumption. And if we make this assumption, then we have two processes. First of all, the process in the gas phase and the process inside the liquid phase. So we were not able to develop a general model of this phenomenon. But at the same time, we developed a model based on a number of additional assumptions. So one of the additional assumptions is the assumptions about the values of the gradients perpendicular to the surface of the droplets and along the surface of the droplets. So we assumed that this gradient of parameters, primarily temperature, along the surface of the droplet is much smaller compared with the gradient perpendicular to the surface of the droplet. And in this case, and also we can separate the process in the liquid phase and in the gas phase. So in this case, we are assuming we need to eliminate from the very beginning the process in supercritical or near critical conditions when the interface between liquid and the gas phase is blurred. Now, our model is, this model which was developed is essentially based on the original model which was developed by our colleague from Italy, Tannini and Casale, who developed the model for the gas phase. So which is based on the solution of this conservation equation, where phi A alpha is mass fraction of a particular species. It could be either vapor or ambient gas. And then these equations were solved by the Italian group, and then under certain additional conditions, they obtained the expressions for the normalized evaporation mass flux at the surface of the droplet, which turned out to be the function of the eccentricity parameter. What we tried to do, we used the solution which was obtained by the Italian group as the boundary condition for the solution to the equations for heat transfer at inside the droplet. And this equation was solved subject to conventional boundary condition, and the value of H was taken from the model developed by the Tonini and Casale, and also the reduction of the movement of the surface of the droplet also was inferred from that model. And also we considered two cases where we considered the case of ablate and prolate spheroids. In both cases, we assumed that the volume of the spheroid is the same as the volume of the sphere of a certain radius r. And this radius r is taken equal to 10 micrometers. And as a result of the calculation, we were able to obtain that initially the temperature, the distribution of temperature depends on the local curvature. So when the local curvature is the maximum, then initially the temperature becomes the highest. And then as time goes on, these temperatures starts leveling down or leveling up. And the same takes place in the case of ablate spheroid. So here we have initial increase of temperature, and then this increase is spreading along all over the surface. And then this is shown, these features are shown on these graphs. As you can see, the temperatures becomes more and more close at various parts of the surface of the droplet, and also droplet itself becomes more spherical during the evaporation process. So these, in a sense, these could justify our initial assumptions that the droplet can be considered as spherical. And at the same time, the total effect of non-sphericity on droplet heating and evaporation appears to be relatively small for the range of parameters which we considered. So having said this, we need to keep in mind that this model was based on the number of assumptions, including the assumption that the shape of the droplet is still close to spherical. It is not very deformed. It is not like a sausage. And the details of the model and its applications are described in our recent paper, which was prepared mainly by my colleague, who is the first co-author. And then when we consider non-spherical droplets, as a limiting case of non-spherical droplets, we can consider liquid film. Liquid film can be considered as a sort of a limiting case of non-spherical droplets. So again, this problem of heating and evaporation of liquid film, including multi-component film, is not a new problem. So it was considered in a number of papers, but I think that the approach which we developed, is more efficient, mainly from the computational point of view compared with the previous approaches. So to start with, the main motivation of this work, again, was linked with the automotive applications. So what happens is that when we have injection of liquid into internal combustion engines, initially you have the formation of spray. But then at some stage it doesn't, the injection stops. And when injection stops, then part of the liquid fuel starts spreading along the surface of along the inner surface of the engine, and then they form a film of fuel, and this film, starts heating and evaporating, and eventually some sort of residuals are formed inside the engines. And so it is quite essential for us for understanding the performance of the engines, and also of trying to understand the underlying process which takes place there, to be able to model these film. And so that was the main motivation why this model was developed in the first place. And once it is developed, it can have a much wider range of applications. So obviously we could not develop, some sort of a very general model, but in fact we don't need it. So we assumed from the very beginning that the film is very thin. That means that we can ignore the conventional processes and use only, and take into account only diffusion process. It could be thermal diffusion, it could be mass diffusion. Also, we ignored from the very beginning the end effects. That is, the effects at the edges of the spray. And once we make these assumptions, then the problem becomes one-dimensional. So that means that the distribution of temperature is inside the film is the function of the distance from the wall inside the film. And it is described by a well-known equation for the temperature, which is solved subject to the boundary condition at the surface of the droplet. These are Robin boundary conditions at the surface of the droplet, and we use the Dirichlet boundary conditions at the wall. And also we took into account the evaporation at the surface of the film by modifying the temperature of the gas. It was done in exactly the same way as we did it for the case of evaporating droplets. And then, we got the analytical solution to this equation. So, obviously, this solution was not used during the whole period of film heating and evaporation, but it was used during a small time step during which the heating and evaporation of film takes place. And if it is used at the small time step, then in fact this solution is incorporated into numerical code. So that means that the main objective of this solution is not to use it in isolation, but to use it as a part of the numerical code. And then for this numerical code, we need to introduce the mass transfer coefficient. And for the mass transfer coefficient, we used this equation linking mass transfer and heat transfer coefficient, which is known as Chilton-Corbin analogy. The value of H, the heat transfer convection coefficient, is assumed to be constant. And in a very similar way, we considered the species diffusion inside the film. So the film is multi-component. And this assumption is absolutely essential for the application to automotive engines, because all automotive fuels are multi-component. There is no such thing as a monocomponent automotive fuel. And in this case, these equation, the solution to this equation is as important as the solution for the heat transfer equation. And these are conventional boundary condition, conventional boundary condition at the surface of the film, which takes into account the evaporation of species. And this is the condition of on the surface of the wall. And then we were able to obtain the analytical solution to this equation, which is shown here. And this analytical solution was incorporated in numerical code. It is valid during the small time step. And then at the end of the time step, we can adjust the value of gas temperature. We can adjust the value of the thickness of the film, and so on. And then, once we have developed this model, it has to be compared with experimental data. And it got some sort of reasonable agreement with them. And more details of this model are described in our recent paper, which was published several months ago, and together with my colleagues. And all details of the models can be obtained from that paper. And now we are moving to the last topic of our presentation, namely modeling of heating and evaporation and ignition. And here we again recall the structure of computational fluid dynamics codes. So we have Lagrangian Eulerian approach. So we forget about Lagrangian approach for the time being. That is, we will not consider the link between the computational cells, but we will focus only on what is going on in each individual cell. And then the process inside these individual cells are described by the system of ordinary differential equations. And this is one of the examples of ordinary differential equations which we considered in one of our previous publications. So this is the equation for the gas temperature. This is the equation for the molar fraction of fuel. This is another equation for the molar fraction of oxidizer, equation for the temperature of droplet, and equation for the droplet radius. So clearly here we have only 5 equations. But in the general case, if we take into account chemical kinetics, for example, or if we take into account the contribution of numerous droplets, the number of these equations could go into hundreds, if not thousands. Now, what to do with these equations? So their direct solution appears to be not only difficult, but also we cannot achieve any reasonable accuracy of this solution. So to progress here, we need to use additional assumptions, and we need to use new approaches. And one of the approaches which we used is based on the method of slow invariant manifold. So without going into details of this method, we can consider this system of equations where x and y are vectors in n-dimensional and m-dimensional space. And epsilon is a small parameter. So if epsilon is sufficiently small, then we don't really need to solve this second equation. And the solution to the second equation could be something very simple, namely the algebraic equation. Thank you. G is equal to 0. Okay? So in this case, we reduce dimension of the system. and reduces quite considerably. And if epsilon is is small but not close to 0, we still can find this equation for the manifold, but this equation will become a little bit more complex. And I am not going to go into the details of this method, and instead I will refer you to the book which was published by colleagues from Samara University, mainly Professor Shepakin and Professor Sobolev. And this is the book which was used in our analysis. And here we have examples of the manifold which are shown for this particular equation. And here we have these equations for the manifold. And the upper branch of this manifold appears to be stable, and the lower branch appears to be unstable, appears to be repelling. And also, we developed the concept of positive environment manifolds for non-Lipschitzian system. And again, you know, this is described in our joint papers with Vladimir and Elena. And I think that we wouldn't require a separate lecture to cover it. And we'll just refer to this paper without giving further details. And this approach can be applied to many ordinary differential equations describing heating, evaporation, and ignition of individual sprays. And again, you know, these applications, the details of the application are described in this paper, and I'm not going to go into further details. And now I will spend a couple of minutes on future challenges. So the full Lagrangian approach is a powerful method, but at the same time, it appears to be rather tricky to apply this method to turbulent sprays. Some initial work in this direction is performed mainly by my colleagues. It's Andreas Papouzakis, and we developed a model for the evolution of droplet cloud in a turbulent flow, but this model is based on a number of rather serious assumptions and limitations, and we are working on a more general mode in which these limitations could be dropped. And then another problem is to consider strongly deformed droplets, because these limitations that the model which we developed for non-spherical droplets is applicable to weakly deformed droplets is a serious limitation. And we are working on developing a more general model, and some ideas of the more general model is described by the paper by Tonini and Casale. And now we are going to apply these ideas to the problem of droplet heating and evaporation. Now, the serious limitations of our model is that all the models are applicable to subcritical state, when we can describe a sharp interface between liquid and gas phase. So the generalization of the model to a supercritical state with a blurred interface is still a challenge. And also the modeling of engineering problems using slow invariant manifold is still a challenge. So we try to make some initial work in this direction many years ago. It was about 17 years ago. But unfortunately, you know, there haven't been any more progress on it, and now we're working in this direction. And this is the acknowledgement, and thank you very much for your attention.
Questions for Brosi?
Yeah.
In the first part of your talk, you mentioned some limitations of the FLA.
Yep. Yep.
And the third limitation was omitting from the account the interaction between
Yep.
the trajectory of particles.
Yep.
How is critical this limitation, and maybe it is forming the direction for the future research?
I can't agree with you more, you know, because it is a critical limitation, because this is, you know, there are no interaction between the droplets, so within the classical full Lagrangian approach. But clearly, there could be a way of how to take them into account as additional development of the model. So for us at the moment, it is not a top priority, because it is much more important for us to still keeping these limitations about the lack of interaction, try to develop the model to take into account the proper effects of turbulence of the Carrier phase. So this is our main focus. But what you mentioned is absolutely important, you know, and we hopefully will work on this in the future. Thank you very much for the question. Yeah?
So I think we have to move on. We are a bit...
Okay.
Thank you for your presentation.
Thank you.
So the next presentation, David Asatryan, you see it there? Armenia, and it will be about image processing again.
In Russian.
Yeah, you will present in Russian? No, you говоришь по-русски? Да.
Прежде всего, хочу поблагодарить организаторов конференции за приглашение. Спасибо. Я приехал из Армении, представляю два учреждения, две организации. Академия наук Армении, Институт информатики, проблем информатики и автоматизации, и Российско-армянский университет. Этот вот он. Университет создан примерно 20 лет тому назад, после развала Советского Союза. Правительство Армении и России предприняли организацию такого университета для того, чтобы здесь, по-моему, я написал выдержку из основополагающих документов, для чего был создан университет. И с тех пор университет финансируется обеими правительствами, функционирует. Довольно большой университет, считается одним из лучших в Армении. И я, значит, прошу мой доклад рассматривать не как последнее слово науки, а просто как попытку представить науку в некоторой узкой области, которой занимаются в университете. Мы нуждаемся в связях с российскими университетами, и данное мероприятие является одним из таких вот фактов, способствующих нашему сотрудничеству. Значит, в названии моего доклада имеется два ключевых слова. Первое – это структурный анализ изображения, такое словосочетание. Ну, конечно же, техника и теория обработки изображений, ну, именно этим и занимается, так сказать. Но здесь нужно отметить, что человек, когда рассматривает, тоже тривиальная мысль, но когда рассматривает изображение, то из него извлекает фактически содержательную, структурную информацию. И вот это обстоятельство побуждает исследователей заниматься в основном, не в основном, а в значительной степени такими задачами, которые приводят к результатам, созвучным с восприятием визуальной системы человека. И вот ну, в конце прошлого столетия в работах американского профессора Бовика и сотрудниками этот факт был немножко так декларирован, и на этой основе было разработано предложение избегать таких методов анализа изображений и оценивания качества изображения, которые основаны на поточечном сравнении и использовании всяких среднеквадратических критериев или похожих на них. И вот это как раз в одной из работ Бовика такая картина нарисована. Ну, второе ключевое слово, конечно, это градиентное поле. Оно очень хорошо известно, очень издавна применяется во многих задачах. Нас интересует тот факт, что градиентное поле, ну, если здесь визуализированное градиентное поле, оно содержит значительную долю информации, которую человек, в общем-то, воспринимает, рассматривая изображение. На этих примерах мы можем убедиться, что, во-первых, легко узнавать как оригинал. Во-вторых, можно различать структурные элементы изображения и практически основные структурные элементы, которые можно использовать как некоторое описание, формальное или там полуформальное описание изображения. Итак, значит, вот мы занимаемся именно вот такими задачами. Это очень маленькая доля тех задач, которыми занимаются в университете. ну, так уж получилось, что я представляю сегодня. Может быть, на следующих конференциях будут другие темы тоже здесь рассмотрены. Значит, я буду рассказывать основные понятия градиентного поля так быстро, значит, пройдем. Далее введем понятие рассеивания, эллипса рассеивания градиентного поля. И на этой основе, значит, предложим понятие доминантного направления или направленности или ориентации изображения. Дальше примем модель для распределения градиентного поля, магнитуды градиента. Далее предложим меру близости двух изображений с использованием вышеназванных понятий. И представлю ряд применений, приложений этих методов. Первое – это оценивание размытости, степени размытости изображения. Далее рассмотрим задачу оценивания качества алгоритмов масштабирования и вращения изображения. Далее, значит, приступим к исследованию, к методам анализа видеопоследовательности. Это сегментация, индексирование и вот такой небольшой интеллектуальный метод интеллектуального анализа видеопоследовательности. И в конце, если останется время, еще одну задачу рассмотрим. Это обнаружение объекта по видеосъемкам беспилотного летательного аппарата. Итак, значит, градиентное поле мы используем таким образом две компоненты, вертикальная и горизонтальная, и магнитуду градиента, там наверху указаны. Расчеты проводим при помощи оператора Соболя, это очень удобно для нас. И в итоге получаем такие выражения, простейшие выражения для компонент градиента. И в этот момент мы, значит, объявляем, что мы градиентное поле принимаем как характеристику структуры изображения. Вот в рамках вот этого понятия и будем дальше двигаться. Здесь приведено выражение для рассеивания, эллипса рассеивания градиентного поля. Простая формула, но вот известно, что здесь вот как раз приведен пример изображения с указанием его эллипса рассеивания. Известно, что главная ось эллипса в этом случае совпадает с линией ортогональной регрессии, а угол, еще есть угол наклона линии регрессии, который здесь обозначено через альфа, и выражение, по которому это определяется. Приведенные примеры, кажется, нас убеждают в том, что понятие корректное, то есть результат расчета угла ориентации и наше визуальное восприятие, в общем-то, согласуются друг с другом. Для распределения магнитуды градиента в литературе имеется много различных подходов, основанных, скажем, на обычное гауссовское, на обобщенное гауссовское распределение, на распределение Вейбула и другие распределения из экспоненциального семейства. Значит, мы остановились на распределении Вейбула, имеются и совсем уж небольшие, так сказать, теоретические предпосылки тоже для этого. Вот выражение распределения, плотности распределения Вейбула, параметры двухпараметрическое, есть и трехпараметрическое распределение Вейбула, но мы двухпараметрически используем. Лямбда параметр – это параметр масштаба, К – параметр формы. Ну, вот это просто пример, который показывает, насколько может быть согласованное распределение Вейбула с гистограммой магнитуд градиента вот такого, скажем, изображения. Параметры распределения определяются методом моментов. Это более удобно. Уравнение метода моментов приведены здесь. Справа показана кривая зависимости левой части верхнего уравнения от параметра k. Такая монотонная зависимость. Это монотонная показывается аналитически. Но этот факт используется для разработки хорошего, удобного или быстрого, достаточно быстрого метода решения нелинейных, вот этих нелинейных уравнений. Далее предлагается вот формула W квадрат. Это зависит от параметров k и лямбда обеих изображений, близость которых оценивается. Здесь мы принимаем такой вот утверждение, что если изображения близки, то близки и градиентные поля. Следовательно, и распределение, которое описывает эти градиентные поля, и, следовательно, и близки значения этих параметров. Обратное, к сожалению, неверно. То есть градиентные поля могут быть очень близки, но изображения будут совершенно различными. Но это нас не смущает, потому что кто занимается обработкой изображений, техникой, знает, что в основном нам нужно бывает сравнивать непроизвольные изображения, чтобы определить их близость, а оригинал и некоторые преобразованные изображения. Если там что-то такое мы выполняем с этими изображениями, хотим понять, насколько близко получается ответ. И вот этот пример, простой пример. Пример А – это оригинал, пример Б – это повернутое, это вращенное на 45 градусов изображение. Ну, не то же самое, а это вырезка из большого изображения, которое мы вращаем. И изображение С, которое это есть увеличенное А в 1,5 раза. Если пользоваться среднеквадратическим критерием, ну, известно, что ПСНР в децибелах определяется для таких случаев. Очень низкий. Кто занимается этими делами, знает, что считается, что если для того, чтобы глаз, визуальная система считала эти изображения одинаковыми или почти одинаковыми, нужно, чтобы ПСНР был больше 30 дБ. Ну, в данном случае это значение очень низкое. Однако вот W квадрат мы видим, что значение его близко к максимально возможному, который есть единица. Есть и другие примеры интересные. Вот это то же самое изображение, просто перевернутое на 180 градусов. Такой же результат. Здесь вот первые два – это вырезки из оригинала, которые отличаются всего на одну строку и на один столбец от оригинала. Ну, для визуальной системы человека это одно и то же, одинаковое изображение. Но расчеты показывают, что PSNR, так сказать, не ловит это сходство, а это W квадрат ловит. Здесь справа просто деформация проведена, тоже, значит, эта деформация практически не влияет на качество изображения, то, что мы глазами видим. Дальше перейдем к приложениям. Значит, первое приложение – это оценивание степени размытости изображения. И очень важное понятие, особенно вот оно используется в технике для оценивания качества видео и фотоаппаратуры. Ну вот сделаем такое микроскопическое теоретическое исследование. Значит, предположим, что изображение пиксели изображения являются выборкой из нормального распределения с параметрами μ и сигма квадрат. Тогда компоненты градиентного поля без модуля имеют такой вид, они будут иметь тоже нормальное распределение и независимые. Известно и легко это доказать, что магнитуда градиента в этом случае будет описываться распределением Релея, так называемым. Но тоже легко убедиться, что распределение Релея – это частный случай распределения Вейбула при значении параметра k равное 2 и лямбда равное сигма корень из 2. Теперь, а что делать, если существует некое распределение для выборки, так сказать, для массива значения интенсивности? Это отличается от нормального. Значит, здесь предлагается, единственное, что можем делать в данном случае, это воспользоваться таким достаточно грубым, наверное, приближением центральной предельной теоремы, которая приведет тоже к нормальному распределению, и утверждать, что тогда вот параметр k будет приблизительно равно 2. Ну, теория, а вот интересно, а что на практике получается? На практике вот что. Вот есть пример, таких примеров очень много. Но вот первый пример, первое изображение – это оригинал. Остальные получены путем сглаживания с монотонно возрастающим значением вот этого фактора сглаживания. А внизу показаны оценки параметра k. Мы видим, что значения тоже монотонно возрастают и приближаются к значению 2. То есть где-то вот близко к тому, что из теории. Внизу показано применение в другой задаче, связанной с размытием. Если нам нужно разделить размытую и неразмытую часть изображения. Это часто бывает, скажем, на заднем плане имеется объект, который размыт, а в переднем плане тот, что нас интересует. Поэтому иногда важно понять, насколько здесь это отличается. Ну вот пример такой, который показывает, что это возможно при помощи данного подхода. Следующая задача – это оценивание качества алгоритмов масштабирования и вращения изображений. В литературе и в интернете тоже можете найти очень много работ в которых эта задача рассматривается. Но в основном, не все, но в основном результат демонстрируется в виде определенного примера, и решение о том, какое изображение лучшего качества, оставляется оператору или вот читателю. Хотя автор говорит, вот, видишь, вот здесь вот этот лучше, чем тот, скажем, алгоритм. То есть возникает необходимость иметь некоторые формальные критерии для оценивания качества таких преобразований. То же самое при вращении происходит. Значит, предлагается такая процедура простая. Вот берем изображение, которое мы в данном случае хотим увеличить или уменьшить, или просто выборку из той базы, которую мы хотим исследовать. Меняем размеры, масштабируем с коэффициентом масштабирования бета. Здесь указано несколько таких значений. И полученные изображения сравниваем с оригиналом. Благо мы можем это делать, поскольку наш критерий, как мы убедились, работает, в принципе, независимо от размера и ориентации сравниваемых изображений. Результат очень интересный, если внимательно рассмотреть и еще анализировать. Но времени нет, чтобы это делать. Но так на глаз видно, что действительно отличаются различные 4 типа алгоритмов масштабирования. Я не помню, по какой программе мы это, по-моему, по Photoshop мы сделали это масштабирование. Действительно, они отличаются, и есть возможность делать выбор. И еще тоже интересно, что при уменьшении или при увеличении изображения эти кривые меняются местами. Это вообще даже непонятно, почему так. Впрочем, это бросает камень, так сказать, в сторону тех работ, которых предлагается для того, чтобы сравнивать различные алгоритмы, сначала увеличивать, потом уменьшить, потом сравнивать по PSNR. Ясно, что это плохо. Мы для этого случая тоже, придумали одно понятие, оно не очень известно. Остаточную ошибку мы назвали люфтом. Люфт backlash для этого метода масштабирования. Далее, приступаем к анализу видеопоследовательности. Сегментация, понятно, это разделение последовательности, видеопоследовательности на однородные, если можно это понятие применить здесь, по содержанию кадры, как показано на рисунке, и точки перехода этих сегментов находятся путем сравнения соседних кадров по близости. Если близость, поскольку кадры все имеют одинаковый размер, общепринятым является применение PSNR, как в предыдущих случаях. Но если делать это при помощи предложенной критерия W квадрат, мы имеем огромное преимущество, о котором сейчас я скажу. Но прежде перейдем к следующей задаче. Это задача индексации, так она называется. Это выбор из каждого сегмента ключевого какого-то кадра, который наилучшим образом характеризует содержание данного сегмента. Ну, ясно, что это делается для того, чтобы потом при поиске из больших баз данных видеопоследовательность определенного содержания легче пользоваться этими ключевыми кадрами, чем просто подряд все, значит, сравнивать. Это очень важная задача. И вот здесь показано это. Если вы выбрали ключевые кадры, мы можем его запомнить вместе с видеопоследовательностью. Это занимает очень мало места, естественно. Ну, несколько порядков меньший объем. Вот. Но если пользоваться вот этой нашей методикой, то есть очень простой способ выбора этого ключевого кадра. Вот здесь показано рассеивание значений параметров, которые использовались при сегментации. Значит, если я уже выбрал сегмент, ставлю эти вещи, и здесь можно сравнивать каждый с каждым даже, кадры каждый с каждым, поскольку тут всего 2 числа надо. Это очень быстрая операция. И найти тот кадр, который ближе всего ко всем остальным. Но есть более простой способ, это просто усреднить значение этих параметров. Ну и полученное значение, конечно, может оказаться, что это среднее то такого кадра с такими параметрами среднего значения может не существовать в последовательности. Но можно выбрать ближайший, конечно. Это очень быстрый алгоритм. Следующее. Вот это предыдущее рассмотрение наводит на такую постановку. Можно считать новую постановку, потому что я не видел в литературе ничего подобного. Но оно так сразу немножко такое не очень, может быть, корректное, не очень хорошо формализуемое. Но вот тут 2 сегмента представлены. Можно рассуждать. Значит, первый сегмент характеризуется тем, что там кадры как бы хаотически меняются. Хотя это одно и то же содержание. Ну, там, может, футбол там показывают, там мяч идет туда-сюда, не знаю. Второй рисунок показывает, что есть достаточно уверенное, достаточно равномерное изменение содержания этого сегмента. По-моему, это может послужить основой для интеллектуального анализа видеопоследовательности в будущем. Этим нас занимается, но сейчас пока вот только это я могу показать. Ну, таких примеров, конечно, много. Мы много смотрели. Действительно, вот на таком уровне формализации это работает, но всегда можно поспорить, если речь идет о конкретном сегменте. Вот. И если время есть, обнаружение объекта по видеосъемкам беспилотного летательного аппарата. Ну, здесь, конечно, показан Google Map. Здесь красной вот этой рамкой обозначено некоторый участок, который мы назвали region of interest, то есть участок или область интереса. То есть мы когда-то сняли, кстати, это тот кусок, это мой дом там расположен в этом. Значит, это когда-то сняли, положили, поставили там в базу, и через определенное время или такая же задача возникает на карте обнаружить этот же участок, или это делать при помощи беспилотного летательного аппарата. В принципе, это одно и то же, но здесь иллюстративный такой пример для того, чтобы показать работу этого метода. Поскольку мы считаем, что размер рассматриваемых участков и их ориентация принципиальной роли не играют, то поиск осуществляется таким образом. При помощи скользящего окна сканируется это изображение, и по максимальной близости определяется этот участок. Ну, здесь он показан, как раз это не построенное так пример, а реально, значит, проведена обработка. Вторая карта, конечно, имеет другой ракурс, другой размер, как это бывает при реальных полетах беспилотника. Разный ракурс может быть и так далее. Вот ответ, первоначальная область и найденная область. Что тут важно, что нас же не интересует, в принципе, вот вся область. Нас интересуют определенные детали, определенные объекты в этой области. И вот видно, что они вполне различимы в данном случае. Конечно, там есть автомобили, которые могут в другое время, они по-другому расположены. Но это всего лишь какая-то небольшая помеха. Все. Спасибо.